Good morning or good afternoon, everybody. Today we'll speak about flexelectricity, but let me start from piezoelectricity. As explained in the next slide, we can take a piece of piezoelectric material, put electrodes on it, connect the electrodes with an ampermeter, and load it mechanically. Then you can register a charge passing through your device, which is proportional to the mechanical load. And that means that the deformation produced by the load induced polarization proportional to the deformation induced. This is the direct piezoelectric effect. Instead of your ampermeter, you can put a source of DC voltage, and you will find your capacitor deformed. There will be change in thickness proportional to the voltage applied. That means that the field inside generates some deformation. This converse effect. And piezoelectricity is very useful phenomena. You can find around us many application of it in, let's say, in mobile phone. It is bandpass filter. You can find even in a car, fuel injector, and so on. And people are pretty happy with the piezoelectricity as an electromechanical phenomena, as the electromechanical coupling. However, they are not absolutely happy. There are two reasons for that. First, piezoelectricity is allowed not in all materials, not in materials of all possible symmetries. Materials should be non-centrosymmetric. On this table you see point groups, crystalline and non-crystalline, and non-centrosymmetric groups are marked with blue and white. Only in these groups piezoelectricity is possible. Not in yellow, and yellow stands for centrosymmetricity. And most of the materials are centrosymmetric, so you're limited with the choice of your material for your piezoelectric application. The second, strong piezoelectric effect can be found only in ferroelectrics, in the ferroelectric phase, where some spontaneous polarization develops. And the spontaneous polarization should be aligned to the sample, more or less. But ferroelectrics like to be split into domains, and this deteriorates the electromechanical response. So it sounds great to find an electromechanical phenomenon which is active in centrosymmetric materials. And here comes the flexelectricity. On the next slide, you see equation for electromechanical response. And here the first term is for the piezoelectric coupling. And the strain and polarization here are linked with a third rank tensor. And the third rank tensor is forbidden in centrosymmetric materials. This is the reason for the limited choice of piezoelectric materials. However, one can conceive a strain gradient as a mechanical driving force. And in this case, a fourth rank tensor will link the strain gradient and polarization. And fourth rank tensor is allowed in materials of any symmetry. Now to test this response, you should bend your sample as shown. below and you collect the charge proportional to the strain gradient. Or you can apply the voltage and the result will be sample bending proportional to the voltage. It sounds absolutely great, something which can be found in centrosymmetric materials. However, clearly flexoelectricity is a high order effect and it is actually extremely weak. However, during the past decades, as is clear from this next slide, people were very interested in this phenomena, and this is a number of publications plotted as a function of years. It's an epidemic type growth. So showing that indeed this phenomena is of interest. And this curve actually serves as a justification of my talk, which will be basically an elementary introduction into flexoelectricity. In my talk, there will be no historical remarks, no references, just simple basic ideas. And before finishing my introduction, I'd like to make a couple of comments. First, one might imagine, from judging from the beginning of my talk, that it is just something of interest for application. No, this is not the case. Flexoelectricity is important information of the phonon spectrum, in the shape of domains, in shape of the structure of domain patterns, structure of domain walls, and many other phenomena. And nowadays, the most interest is to the physics behind the ferroelectricity. Second, the name flexoelectricity implies some bending, and I gave you an example where sample was bent to produce strain gradient. However, it's not the only possibility. You can use a truncated pyramid as a sample, and inside you will generate strain gradient and you can test flexoelectricity. In my talk, I will be comparing all the time piezoelectricity with flexoelectricity to find that the latter is very different from the former. There are two basic features of piezoelectricity. First, if you are interested in piezoelectricity in a running wave, like in a bandpass filter, you need a piezoelectric coefficient, and this coefficient can be measured under conditions of static homogeneous stressing of the sample. So one piezoelectric coefficient controls piezoelectricity in these two cases. Second, piezoelectricity is basically a bulk effect. Unless your sample is very, very thin, you can forget about structure of the surface. It's the bulk which controls the effect. These two features cannot be found in flexoelectricity. The flexoelectric response in the running wave and in a static experiment is different. And in a bulk sample, you can modify the surface and you can essentially modify the total flexoelectric effect. Let's start with static bulk effect. Let's take the first column. Let's take a centrosymmetric material and apply a homogeneous deformation. And you will find displacement of all atoms, and displacement of all atoms will be proportional to the distance to these atoms from a fixed point. I call this kind of deformation, okay, displacement of atoms, elastic theory approximation for the atom displacement. And it is known that in centrosymmetric materials there is no piezoelectricity, so you displace atom but you produce no polarization response. Now let's take a piezoelectric non-centrosymmetric material. Now the material is not ready to follow elastic theory approximation, and there is some disagreement in the displacement, and it is called internal strain. So the difference between the real position of atom and its position in the elastic theory approximation. And you can multiply internal strains with the charges, sum up of the unit cell, and you will get the polarization response. Now, flexoelectric effect. You take a centrosymmetric crystal, and here you cannot find internal strains proportional to the strain, but the material is not ready under a strain gradient to follow elastic theory approximation, and there is some disagreement, some internal strain. Okay, using this strain also you can calculate the flexoelectric response. This is microscopics. Now about description. This typical way to describe, practical way, is to use thermodynamics. One consider a thermodynamic potential shown here. First, let's see how this method works for piezoelectricity. Here you find the first term, which is energy of internal strain. Second, it is a coupling between the polarization and strain. Okay, clearly all suffixes are dropped for simplicity. And the third term, it's coupling to the electric field. You minimize your thermodynamic potential and you get equation for the response of polarization, where the first term is a dielectric response and the second term is the piezoelectric response. Now, for flexoelectricity, the story is very similar. The difference is now the electromechanical coupling term contains a product of polarization and the strain gradient. You apply the same procedure and you get the equation for the flexoelectric response. And here an important feature comes. The flexoelectric constant mu is found to be proportional to the dielectric susceptibility. That means if you take a ferroelectric above the transition, where it is centrosymmetric typically, you should find an enormously strong flexoelectric response. And indeed that was shown experimentally. In this material, in barium strontium titanate, the maximum dielectric constant is 20,000, and you see that the temperature dependence of flexoelectric coefficient is identical to that of the dielectric constant. By now, their piezoelectricity and flexoelectricity look a lot alike. Now, dynamic effect. Let's consider a harmonic wave, acoustic wave propagating in a sample, and with very good accuracy, displacement of the atoms are proportional to a sinus. I called this way I call it elastic theory approximation for displacement of the atoms. It's very good approximation actually. You find displacement of charges, but there is no polarization wave generated. But crystals do not like to follow exactly this approximation, and in piezoelectrics you find some disagreement. Again, internal strains, it is deviation from elastic theory approximation. It is actually the same internal strain that we discussed in the previous section, and you generate polarization wave. Now let's pass to a center symmetric crystal. There is no linear in the strain contribution to the internal strains. But we know, but in this case, we have internal strains proportional to the strain gradient, as was discussed before, but this is not the end of the story. In our wave, material moves with acceleration, and in this case, it matters that the atoms are of different mass, and because of that, additional internal strain, additional deviation from elastic theory approximation appears. So it will be internal strain, which is proportional to acceleration and mass difference. It is in this simple case of 2 atoms per unit cell. But the acceleration is proportional to the strain gradient. Thus, because of this effect, we generate additional contribution to internal strain proportional to the strain gradient. This is dynamic flexoelectric effect. Okay, appreciable difference compared to the piezoelectric case. Now, surface effect. Let's consider piezoelectric. Piezoelectric material, here it is marked with green. At the interface, you have material is modified, but it is also piezoelectric, but it's different from the bulk. But nothing new. It's just maybe surface layer which doesn't work properly. If we pass to a center symmetric material, the situation is completely different. The inner part is non-piezoelectric, but at the interface, the symmetry is broken by the presence of the interface, and one expects to have a thin piezoelectric layer. Okay, maybe at least one lattice constant, 2 lattice constant, and 2 sides. And the sign of the piezoelectric coefficient is opposite because of the opposite sign of the normal to the top and bottom surfaces of the sample. And these layers contributes a lot in our response. Let's see how it happens. Let's consider a vertical strain gradient. Okay, let it be on the middle plane. The strain is 0. Then, at the top layer, the strain will be equal to the strain gradient multiplied by half thickness, and at the bottom, the same absolute value, but the sign is opposite. Now, if we calculate the polarization, piezoelectric polarization generated, you will find that it is the same. Here you have 2 times minus, and the product of them will give us plus. Let us see how this polarization works in the total flexoelectric response. Next slide is a bit busy, but I think we will manage. You connect, to measure the response, you connect electrodes on 2 sides with an ampermeter, and then pay attention to the fields inside. Actually, the whole system is short-circuited, but the piezoelectric layer if it is thin enough, can be considered as actually open circuit, because the electrode short circuit is very far from it. And as a result, the polarization will generate a depolarizing field shown in the frame. Now we should take into account that system is short-circuited, the total drop of the potential is zero, which is explained in the next line in the frame. So the field in the layers will generate field inside. And remarkably, the field inside occurs to be thickness independent of thickness of the sample. So it is a surface stimulated effect which is actually independent of the thickness of the sample. And now to calculate polarization, you should multiply this field with the dielectric permittivity for the inner part of our sample, centrosymmetric part. And this way we get a flexoelectric contribution with a flexoelectric constant which is proportional to the bulk dielectric permittivity. And this is absolutely remarkable. This is effect driven by the interface. However, the flexoelectric response scales as a bulk dielectric constant. So all in all, we have three contributions, and two of them are active in acoustic wave, two of them are active in a finite sample, and one can show that static and dynamic contribution are of the same order of magnitude. And what is really remarkable is that if we assume that the thickness of the surface layer about, let's say, a lattice constant, and we take standard value of the piezoelectric coefficient, we will find the same value of the surface of mu surface as for the bulk. So three contributions are comparable, and all of them are proportional to the bulk dielectric constant. Now, a few words about the strengths of the effect. It's a good way to characterize it is calculating the ratio of the flexoelectric coefficient divided by the bulk dielectric constant. And order of magnitude estimates provide us with values of few volts for F. People actually tried to calculate a flexoelectric coefficient from using ab initio calculation. Here I should confess that there is no appreciable progress in this. Still we have papers with very different values of flexoelectric coefficient calculated for the same material. Now, experiment. It was nicely studied strontium titanate, single crystal of strontium titanate, with the values of F about few volts as it should be. However, when people characterize ceramics, and actually that they found enormous value of F, 2-3 orders above the expected value, and actually that was found in maybe in the first serious paper on experimental characterization of flexoelectricity. And I would say because of this large value, effect was recognized as something of interest for application, and that was in reality starting point for the activity in the field. And I will finish my talk with an application-related issue. Using this material, people managed to construct a piezoelectric element made of non-piezoelectrics. You see, this structure is clearly explained this. And they managed to measure a piezoelectric coefficient larger than in quartz. But I should tell you that in quartz, the effect is quite weak. So for the moment, we have no proofs that flexoelectricity can compete with piezoelectricity. And now my conclusions. Flexoelectricity involves interesting physics. Theory, I think, is quite poor, and theory and experiment are far away from each other. Remarkable feature is that flexoelectricity is a surface sensitive effect. That means if you'd like to find a good material for application, you should care not about the bulk, but about the surface. And the bottom line is many things to do are left in theory, experiment, and practice. Thank you for your attention.